So let's prove the Cauchy-Schwarz inequality, sometimes also known as the Cauchy-Bunyakovsky Schwarz inequality. So this is the inequality given two vectors in a vector space and an inner product which is basically something that defines the angle between two elements in a vector space. So the dot product is an example of an inner product. So there are three properties for an inner product. One is positive definiteness, meaning the inner product of something with itself is positive and not zero. So this is going to give us the norm of x squared, actually. So if we're thinking of the dot product, then x dot itself is the length of x squared. And we need linearity, so we need to be able to distribute like so, and then we need conjugate symmetry, which means that if we flip the inner product, we get the complex conjugate if this is a complex inner product. But for a real inner product, the conjugate of a real number is just the same number. So given an inner product space, so that's just a vector space with an inner product on it, so R2 or R3 with the dot product as an example, then we will get the Cauchy-Schwarz inequality, which is that the modulus, which for a complex number, that's just the length of the complex number, but if it's a real inner product, that's just the absolute value. And if it's squared, we don't need the absolute value, it's anyways, right? But that would be less than or equal to the product of the norms. The inner products with themselves, these are the norms. Okay, so the proof. So start off by assuming x and y are not the zero vector, because if they were, if either one was, this inequality would be obviously true, because the inner product of anything with 0 is 0, and then we'd also get a 0 on the right hand side of the equation, and so we get 0 is less than or equal to 0. And so let's define a third element as the projection of x onto y. So if we have two vectors, x and y, and we project x onto y, this is the projection of x onto y, we'll call that z. Well, the way we get the projection is we first project the magnitude, so that's x inner product y, and then we multiply that by, oh, and we need to project that onto the unit vector of y, so we need to divide by the magnitude of y. But that's just a number right now, this is just the magnitude of that vector, so we again need to multiply it by the unit vector of y. But we know that the norm squared is just the inner product with itself, so we can write y inner product y on the bottom. And you might recognize this as the formula we would use for the dot product to get the projection. So next what we're going to do is we're going to subtract this projection from x, which would be this vector, this vertical vector here, and we're going to show that that is orthogonal to y, so that we can then use the Pythagorean theorem. Sorry, this is z. We can then use the Pythagorean theorem for this triangle, where we decompose x into the component parallel to y and the component perpendicular to y to get all of x. And we'll use the Pythagorean theorem to prove the Cauchy-Schwarz inequality. So first we need to show that x minus z is indeed orthogonal to y, and that means the inner product is 0, and that's by definition. So think of the dot product. If two vectors are orthogonal, then the dot product is 0 because cosine of the angle between them is 90 degrees, so you get 0. So writing this out, we know that z is the projection of x onto y, and by linearity of the inner product, we have the following. And since y was not 0, we can cancel that because of the positive definiteness of the inner product. We know inner product of y with itself, or in other words, the norm of y is not 0. And well, we're just subtracting the same thing from itself, so we get 0. And so indeed these are orthogonal. And just a quick side note on why orthogonality gives us the Pythagorean theorem, or in other words, the Pythagorean theorem can be generalized to inner product spaces, is because if we have two vectors u and v that are orthogonal, and so maybe I shouldn't draw the right angle. So when we say orthogonal, it just means that their inner product is 0 in general. For the dot product, or R3, R2 or R3, or a Euclidean space, that means 90 degrees, but in general it just means that their inner product is 0. So that it doesn't have to mean that their angle is 90 degrees. But if we do have orthogonality, then the length of the vector sum we know can be given by the inner product of it with itself, which we can then distribute well, since uv is 0 and vu is the conjugate of uv, but uv is 0 and the conjugate of 0 is also 0, so this is also 0. And so what do we have left? Well, we just have uu and vv, which is the norm of u squared plus the norm of v squared, which is the Pythagorean theorem. So then we can use the Pythagorean theorem, which says that the norm of x squared must be equal to the norm of z squared plus the norm of x minus z squared. which is we can pull out the modulus of this, because this is just a number, and then we have the norm of y squared, and then we have the norm of x minus z squared, and since the bottom here is the norm of y squared, then this is the norm of y to the fourth, and then we can cancel two of those. And because this norm has to be positive, this norm of x minus z squared, this is, well, positive or 0 because it's a norm, or you can also think of it as the inner product of x minus z with itself, which is greater than 0 unless this number is 0. So this is adding something, so this is greater than or equal to just the first term. And so going all the way back to the left-hand side, just rewriting it to clean things up here, what we have is that the norm of x squared is greater than or equal to the modulus of the inner product squared over the norm of y squared, and hence, rearranging, we have that the modulus of x with y squared is less than or equal to the product of the squares of the norms. So we've shown the inequality, but there's also another property of this inequality, and that is that we get the equality here if and only if x is parallel to y, or in other words, x is some scalar multiple of y. So to see this, if we go back to this term, the x minus z, and we look at the picture, this x minus z term is 0 if and only if x is parallel to y, because we got this perpendicular term by subtracting the projection, but if it's already parallel, there is no orthogonal term. And therefore, we, instead of an inequality here, we're just going to get equality. And that's if and only if there is no orthogonal component of x to y. And we can also write this inequality without the squares, so that just says that the modulus of the inner product is less than or equal to the product of the norms. Or, for the dot product formula, we get that the dot product of x with y is less than or equal to the product of the norms. Well, that's because x dot y is the product of the norms times the cosine of the angle between them, and cosine of theta is less than or equal to 1 with equality if and only if theta equals 0, or in other words, the vectors are in the same direction. X is parallel to y. And that's all. Thanks for watching. Make sure to like and subscribe, leave a comment, let me know what else you'd like to see, and don't forget to check out westworks47.com for applied math consulting and math and physics tutoring. Take care.